Hello students, welcome to your favorite PW Gulf and I am Tanya. Today we are going to have the ultimate recap of your chapter electricity. This is your third chapter in physics and when you move in class 10th, right, certainly there are 4 basic chapters. Yeah, we have summarized the 2 chapters before and today we are going to talk about electricity. This term you have heard a lot. Right, we hear this term in our day-to-day lives also, but what is the meaning of this term electricity? Now electricity, electrons, somewhere or the other electrons are involved. How electrons are involved? What is electric current? What is the difference between electric current and current? What is voltage? What is a resistor? All these things we are going to talk about. So take out a paper and pencil and let's start with the basic itself as it is a recap. Yes, there will be numericals also. I will solve the numericals for you and with you certainly practice each and everything that we are going to talk about. So without any further ado, let's start with the basic. Okay. So when we talk about electricity, the term electron pops up. Fine. Right, electricity, electric current, how they are similar? You can say electricity is a generalized raw term. Yeah, and we use this term in place of electric current itself by far now till here. Okay, so electricity is a broader term, a raw term that we are using, and electric current turns out to be a better refined one. How refined one? For understanding of electric current, we need to talk about the basic concept of charge. All of you, everything around you is made up of matter. Table, chair, pen, paper, pencil, air, everything around you is made up of matter. Matter is what? Anything that occupies volume, certainly has space and has a particular amount of mass in it. Mass and volume. So, when we are talking about matter, yes, matter is made up of molecules. Molecules are made up of atoms. When you are going to dig deep, you can see that, okay, inside atom, there is a positive center called as nucleus and around the nucleus in particular orbits or electrons are revolving. Okay, electrons negative in nature, certainly protons are positive in nature and neutrons are also there. So, if I draw, so here neutron and proton and then in the orbit you can see electrons. Okay, this is like class 8th basic, I know. You also know. So, how we are going to take this thing from here? Everyone, when we talk about charge, charge is nothing but a property of matter. That means if I am talking about mass, okay, so I am saying that okay, a body is having certain amount of mass, is it? Whenever I will say mass, one property that actually is dependent on mass, that will be inertia. Okay, similar manner, if I am talking about charge, charge is nothing but a property that will lead to attraction or repulsion. So, when we say charge is nothing but a property of matter, certainly a quantity also. Yes, you can find charge, you can calculate it, I will tell you. But it is nothing but a property. What it will do, it is going to attract or repel the objects. So when we say attraction, repulsion, so we see these things, no? There's a scale and we are going to rub it there on our head and try to bring it closer to the bits of paper. The bits of paper, they are going to get attracted on the plastic scale. How this attraction is taking place? Because of charge, because of this property that is arising. So all of you by far now, yes, charge is nothing but a property. Okay, you can calculate it, I can calculate it, a physical quantity. Yeah, moreover, what it will do, attraction and repulsion, these are the two things everyone, yes, your charge or the property of matter that is able to attract or repel the other object. Okay, attract or repel. Now, I am saying attraction, repulsion. Certainly, for attraction and for repulsion, there should be 2 types of charges. No, yes, we have 2 types of charges. Yes, we have a positive and a negatively charged body. So you can say, okay, positively charged body or negative charge, negatively charged body or positive charge, negative charge. Okay, whatever attraction is taking place, whatever repulsion is taking place, my charge is important for it. Okay, without charges, nothing can happen. Am I clear? Matter is there, charge will be there. This is your truth. I cannot deny that. You cannot deny that. Mass will be there, volume will be there, matter there, no. Similar way. Right? Now, I am saying positive charge, negative charge. We have studied in class 8th. Okay, positive and negative attract each other. Of course, opposite charge. Opposite charges, they are going to attract. Similar way, similar charges, unlike charges. Yes, what will happen? See, unlike charges. Yes, unlike attraction. And like and similar repulsion. Positive, positive repel, negative, negative repel. Now, when I am talking about charge, yes, what is the smallest charge? The smallest charge that I can find is nothing. Let me tell you the amount also for it. Okay, that will be this. 1.6 into 10 to the power minus 19 coulomb. This is the smallest charge I can find, and this is nothing but on your electron. 1 electron. Right? Now, if I am telling you that, okay, this is the smallest amount of charge that I am able to find, certainly a quantity, okay, unit is there. What is the unit? Coulomb. So, whenever you are going to talk about charge, of course, you are going to use this unit, coulomb, capital C is the symbol. When you are saying, no, okay, ma'am, I am having 2 coulomb of charge, that is automatically telling me, okay, you are talking about charge. Okay, that is how we proceed also. Right? Now, this is the unit for my electric charge. Now you are going to get confused that, ma'am, you are saying positive charge, you are saying negative charge. So you are only talking about proton over here. Why so? Kids, when you are going to move in your higher standards, by far now 1.6 into 10 to the power minus 19 coulomb, okay, for electron. In a proper manner, if I say negative, yeah, because of electron, in a proton the same amount but for positive. But yes, by far now, it is here, by far now, this negative sign is not, important for us. Okay, so we are going to talk about 1 electron is nothing but 1.6 into 10 to the power minus 19 coulomb only. No need to use this negative for your standard. Yeah, all the things are going to come in class 12th only. Okay, now as we are through with this, of course, I need to have a symbol. I want to talk about charge, right? I require a symbol. How should I denote a charge? Q, capital Q. Now, taking this thing only forward, we are going to talk about quantization of charge. Everyone, this is nothing but a property, or you can say a general truth that comes with charge. All of you, first of all, going ahead, what is the symbol for charge? Q. Now, the smallest charge I can find that on electron, and it will be 1.6 into 10 to the power minus 19 coulomb. You have to memorize this. Okay. Now, what is this quantization? Everyone, let us break this thing in a very, very general manner. Okay. I am writing my exam. I want a pen. I want to write my exam. I want a pen. Okay. So, I am going to a stationery shop. Now, I am telling that vendor, give me a pen. He's like, okay, fine, take 1 pen. Alright. Now, then and there, I am thinking that, okay, my test is not that long. I just require half a ink in my pen. So, will I tell my vendor, okay, take out half of the ink from here and give me only half of the ink? No, right? He will say, you want to buy a pen, right? I can give you either 1 or no pen, or 2. But I cannot give you half ink of the pen. Or, certainly the ink can be broken down to half. Similar way, if you are eating something and you feel like eating an apple, you are going to go and eat 1 apple. And if you don't want to eat the whole apple, you are going to say that, okay, I am not able to eat the whole apple, I'll keep half. But here, when you are going to a vendor and you will ask, okay, give me half of the apple, he won't give you half of the apple. He'll say that, okay, I am bounded. I will give you either 1 or 2 or 3 or a dozen. But yes, I cannot provide you half the apple or 1.5 apple or 2.5 apples. Similar way, quantization of charge is nothing but, quant means nothing but a packet. My charges are going to be provided to me in a bounded manner. I want a charge. So certainly the smallest charge is nothing but okay on 1 electron that I can get. That is nothing but 1.6 into 10 to the power minus 19 coulomb. Fine by me. Now, I want to find out the charge on 2 electron. So, yes, 2 electron, 2 into 1.6 into 10 to the power minus 19 coulomb. So, I will get 3.2 into 10 to the power minus 19 coulomb. Similar way for 4 electron, 4 into 1.6 into 10 to the power minus 19 coulomb. This thing will go on. And if I will ask you kids that okay, in this particular scenario, can I get 3 into 10 to the power minus 19 coulomb? Can I get 2 into 10 to the power minus 19 coulomb? No, you won't. If I will ask, 2 into 10 to the power minus 19 coulomb charge I require, you will say, ma'am, I can either provide you 1 electron or 2 electron or 3 electron. I can give you electrons in the natural numbers sort of form. Similar way, yes, these are bounded in a certain manner that you won't be able to get 1.5 electron, 2.5 electron. Am I clear, everyone? So quantization of charge is nothing but when we are talking about total or net charge on a body and there are more electrons on it, over there, yes, we are bounded that okay, the number of the electron, they should be in the natural form and no decimal, no half, no 1/4, they are going to work over there. So if I am talking about that, okay, I am having a body, lot of electrons are here, I want to talk about the total charge, Q net. So in simple manner, you are going to say, you have to take out the number of electrons and multiply it with the charge of 1 electron. That's it. So the formula will turn out to be Q is equals to Ne. N is the number of electron. And E is nothing but the charge on a particular electron. So on my pen there are 100 electron. Right? I want to find out what is the total charge on it. What you are going to do? 100 into 1.6 into 10 to the power minus 19 coulomb. That will be the total charge. That will be the net charge. Okay, everyone. So when we talk about quantization, we are bounding ourselves that okay, electrons are there, but they will be in a packet form, bounded form, in the natural number set form, and you cannot have half of the electron or 1/4 of the electron. You cannot break an electron into half, right? That is not possible. Okay, so quantization is nothing but the property that my charges are bounded by, and certainly when we have to find out the net charge or the charge on a particular body. Formula, everyone, the first formula and the most important one, Q is equals to Ne. Q is equals to Ne, and E of course you should memorize. Okay, now as we are getting comfortable, so when we say that okay, as we are getting comfortable, certainly there is one question that usually is asked. So what is that question? The question is that when we are talking about a particular charge, okay, so 1 electron is there, certainly everything is fine, but in the question they are going to ask you that okay, the charge is 1 coulomb, find out the number of electron. How many electrons are there? This is one of the most famous questions that is actually asked. So in this scenario, you are comfortable with the formula. Okay, the formula will be nothing but Q is equals to Ne. So if I erase this portion over here, Q is equals to Ne. Okay, charge is given to me 1 coulomb. They are talking about the number of electron. I know on a particular electron 1.6 into 10 to the power minus 19 coulomb. Comfortable, no? Okay. Fine. Now find out the number of electron. How you are going to solve it? 1 by 1.6 into 10 to the power minus 19. Right? Solve this thing up. Okay. 10 by 16. Yeah. After solving this, of course, take the 0 from here. 16 into 10 to the power 18. Your final n, and yes, I want you all to write that down also there in the chat. Do it. Don't wait for me. So 6.25 into 10 to the power 18 electrons. Can you actually imagine the amount? For 1 coulomb, have a look on the number of electrons. 6.25 into 10 to the power 18 electrons. Okay, this is the number of electrons that you have found. Yeah. So yes, question can come like this also. They are going to ask you, okay, in 4 coulomb, how many electrons are there? In 16 coulomb, how many electrons are there? So you should be comfortable enough with the formula. Here, Q is the net charge, N is the number of electron, and E is nothing but the charge on a particular electron. Okay, now taking this thing only forward, we are going to talk about nothing but a question. So all of you, my advice will be read the question. I will also solve it. Read the question, solve it on your paper, pencil, and then share your answers with me also, and then you can check also. Okay, the question is calculate number of electrons in 2 coulomb charge. Again, they are not talking about anything else. They want that, okay, how many electrons are there? Number of electrons they are concerned with. So what we are going to do, as here in the question only, 2 coulomb, okay, N, number of electrons you have to find, into 1.6 into 10 to the power minus 19. Okay, so 2 by 1.6 into 10 to the power minus 19 N, solve it. And yes, you should be thorough. By far now, kids, you should be thorough with the calculations. Okay, this is the basic thing. Yes, this type of calculation. Now, after solving this, N will come out to be 12.5 into 10 to the power 18. These many electrons for 2 coulomb of charge. Okay, I believe we are through till here, and certainly we are able to solve the questions also. So now we are going to take the things forward and talk about your favorite term, my favorite term, electric current. Everyone, electric current, okay. Kids usually say, okay, current is here. Now, let me clear this difference first of all. That what is the difference between current and electric current? Yes, these two terms, they are not the same. You can say there's a subdivision. But yes, these two terms, they are not same. So when we talk about current as such, current in simple terms is nothing but a flow. Flow of particle. I am not concerned what particle it is. Electron, be it water particle, be it air particle. Flow of particle or rate of flow of particle. So when I say current can be air current can be water current can be electric current also. Now, what exactly electric current would be? When we talk about electric current, kids, over here, certainly we are being specific. How? Electric current, that means flow of electrons I am concerned. I don't care water, I don't care air. Right now I am concerned with electrons. So whenever you use this term at your home or at your school or anywhere else and you are using this term, no, current, that is wrong. Why so? Because you are generalizing. Right? You are saying current is flowing in the wire. People are going to understand you, but in terms of physics or when you are talking, right, certainly you are not being specific. People can say, okay, any type of current. How should we know? So, when we talk about electric current, everyone, yes, electric current will tell you flow of electron particular. Water current, flow of water particle. Air current, flow of air particle. Now, in electric current, yes, electric, that means electron. So, here we are concerned with flow of electron. Yes, rate of flow of electron. Now, I will take something from here, no? And we are going to talk on that. So, everyone, now, I want you to think on the term that we have actually had a word on. That is nothing but speed. Of course, you can talk about velocity also if you are comfortable with it. Okay, so yes, you can see the video of class 9th also if you are getting confused what exactly speed is. So when we talk about speed, it is nothing but the rate of a body covering a particular distance. in unit time. That is speed. How fast, how slow a body is moving, that would be speed. So when I say over here electric current, I am concerned with flow of electron, but I am more concerned with the rate of flow of electron. So if I am emphasizing on the term rate, right, that means my electron flowing, okay, charge flowing, but yes, over here how quickly charge is flowing, that also matters. So if I'm having a wire and inside my wire particles are flowing, how quickly the particles are flowing, that matters. Amount of charge, of course, that will matter. Yes, there are two wires, no. Okay, two wires and I am having a look on a particular region. Okay, electrons are flowing and we are just considering them for 1 second. Here 6 you can say charges are flowing. Okay, 6 charges, 6 coulomb, and over here 16 coulomb. Now have a look in 1 second. Yes, ma'am, more amount of charges flowing through, more current, that matters. But how quickly the charge is flowing, that also matters. That is why over here, see, rate of flow of charges, rate, how quickly. So two things are very, very important. Electric current, yes, you are concerned with flow of electrons, flow of charges. Moreover, you are concerned with how much charge is flowing through. And quickly, of course, as I told you, right? Rate, yes. So I am concerned how quickly the charge will flow. That is a major factor playing over here. Charges are going to flow there in the conductor. I am okay, like okay, conductors, they are going to allow the electric current to move through them. How and everything that we are going to talk about. But how quickly that is taking place, no? That also matters. So rate of flow of electrons inside a conductor taking place, quickly taking place, forming or stating electric current. Okay, so when I say stating electric current, certainly here you are just concerned with the flow, and I will show you also that how this flow is very, very important. Okay, so when I am saying rate of flow of charge in simple terms, how the formula will look like? Charge over time, right? Flow of charge, charge is important, rate of course by time. So my current I is equals to Q by T. Current symbol is nothing but I. I is the symbol for current that we use. Okay, so Q charge, right? T time, rate of flow of charge. So rate, everyone, yeah, rate will come on to the denominator, right? We say no in speed also, in velocity also, right? So similar scenario, yeah, and who is doing that charge? So charge in the numerator itself, or you are concerned with charge flowing in a particular time. That is what is there, charge flowing in a particular time. Okay, I can calculate electric current. Yes, there are instruments also. Moreover, I can find this out. Physical quantity. Okay, now till your standard, everyone, if I ask you what my electric current will be, lot of you will say that okay, it is a vector quantity. No. Till your standard, yes, electric current is nothing but a scalar quantity. Okay, in your exam, the options are going to come, you are going to mark scalar quantity only, having magnitude itself, not concerned with the direction at all. In your higher standards you are going to move, then you are going to understand that okay, electric current is nothing but a tensor quantity. We are going to have a discussion on that, but in some other class, because then we are going to take the other road and then all the things that we have to do. We are not going to do that. Okay, so yes, till your standard you are going to say electric current would be a scalar quantity, no direction important, only magnitude enough. Okay, now come over here. I can find out current. I can do that. There should be a symbol. What is the symbol? Yes, the symbol is I. What is the unit then? The SI unit. The SI unit, everyone, of electric current is nothing but ampere. Capital A would be the symbol. So when I am saying 2 ampere of current, it is automatically understood I am talking about electric current. Okay, similar way 12 ampere electric current. Right? Now, if you are going to have a look here on the formula itself, you are going to say, ma'am, you are saying ampere. But from the formula, if we closely look onto it, right, have a look, we can see that, okay, charge SI unit coulomb, time SI unit second. So from the formula we are getting one more unit, that is coulomb per second. Yes kids, 1 ampere is nothing but 1 coulomb by 1 second. Indeed, that's fine. Why? And in exam, yes, there is this question that is usually asked, that define 1 ampere. What is 1 ampere? 1 ampere is nothing but when 1 coulomb of charge is flowing through my conductor in 1 second. Simple. Okay, when 1 coulomb of charge is flowing through my conductor and taking 1 second, certainly 1 ampere of current is there. Okay, now the question is, 6 coulomb of charge flowing through the conductor A taking 1 second. So the current over here, electric current, that would be 6 ampere. Similarly here, 16 ampere. Okay, pretty much simple. So yes, we are concerned with current. So yeah, we are going to talk about it in a general manner only. Now, as we are through with this, now the question is, if in my exam they are not providing me 6 coulomb, they are just telling me that okay, 4 electrons are passing through a conductor and taking 1 second, what is the current? In that condition, what you are going to do? We have done one formula. Now the first formula, Q is equals to NE, right? Can I place it over here and can I get one more formula? So have a look over here, everyone. If in a place of charge, I can write down NE by T. So I is equals to NE by T. Another formula. Okay, from, see, in physics, yes, everything is interlinked. Moreover, you cannot forget anything. So it is like no beads in a necklace. So yes, you have to stick on to the one, then other one, then another one. So yes, you are going to see the relationships coming also. So don't forget that okay, I know only one formula, I'll be sticking on to it. Yes, you can improvise also. Okay, be a bit flexible and try to improvise the thing and have a look on the things in a different manner also. Alright, now as you are through with electric current, yes, this is very important. Conventional direction of electric current. All of you know what happened when this electric current concept was there. So people at that moment of time, they were pretty much into that, okay, in this world positive is there, only positives. So they were not aware that okay, the electrons, they are actually flowing. They said that okay, electricity is there, no, it is going to move from the positive to the negative only. So people, what they did was, they said that okay, my electric current in the battery also, you are going to see, right, this is the symbol, yeah, positive terminal and the negative terminal. Okay, so current is going to flow from the positive terminal to the negative terminal like this. Okay, like this. So they were unaware that it is nothing but the electrons that are moving. So all of you, I will be talking about that also, and then we are going to jump on to this thing again. We say that current is moving from positive to negative terminal. This is the conventional way, the conventional current you are talking about. The actual electronic current moves from the negative terminal to the positive terminal. Why? All of you right now, you have only studied, right, that what is the flow? The flow of charges. What are the charges? Electrons. So of course electrons are going to move from negative terminal to positive. Okay, so when you will talk about electronic current, it will be in the opposite direction, or in simple terms, electronic current, if I write down, right, electronic current, yeah, the actual one, electron moving negative to positive. The conventional one, yes, our scientists, they have actually given something. So yes, we are bounded by that. We are not changing it. So the conventional current that we all talk about and that we will be talking about and we are going to talk about. So yes, conventional current, the general one that you say, positive to negative. That is why the confusion actually takes place. Okay, by far now stick on to one thing, that okay ma'am, positive to negative, alright. Okay, I know this thing from my basic standard, right, positive to negative. I will show you how the things are going to interline with each other. Okay, let me give a small clarity on that. Before that, a question we are going to do. So everyone, if the amount of charge passing through the cell in 4 minutes is 480 coulomb, calculate the current here passing through the cell. Simple question. So yes, direct formula, I is equals to Q by T. Q given to you 480 coulomb, time given to you 4 minutes. All of you, SI unit, we never change the unit, yeah, to any other form. Okay, so here 4 minute, right, convert into second. First step. Lot of kids, they are going to place 4 directly over here, solve the question, give the answer. That is wrong. 4 minute, all of you, 1 ampere is 1 coulomb by 1 second, no? So second, right? 1 minute is 60 seconds, 4 minute will be 240. Now you can solve. Of course, you can actually do it. So simple. 2 ampere. Okay, keep the things this simple only. Am I clear, everyone? I hope the things are clear to all of you. Now, there are some smaller units also, so I think that I should share those as well. You will find 1 milliampere and 1 microampere. Okay, so 1 milliampere is nothing but 10 to the power minus 3 ampere. Micro is 10 to the power minus 6 ampere. You can just note this thing up, right, for your betterment. Yeah, in questions, yes, they can share the values in milliampere or microampere, so you have to convert. Okay, you cannot directly use it. Yes, SI, you have to follow SI. SI is the standard one. Ammeter. So what is this? Ammeter something. Yes, this is a device that will actually measure current. Okay, so my device that is used to measure the current flowing in my circuit, that would be nothing but ammeter. Speciality ammeter is having. What is a speciality? Yes, your ammeter is always connected in my circuit in a series. What do you mean by series? Just after another. Okay, so when you talk about series, right, so it will come out to be like this. Okay, so this is your circuit, right? Yeah, bulb like this. Okay, series manner. Now, when you are saying that, okay, the ammeter is there, certainly, you know, yes, it will actually show and give the values of the current. There are ammeters as well. They will give the value of current in milliampere. Here, the natural one, the direct one, ammeter, it will give the value in ampere. Okay, the current that is flowing through your circuit. Yeah, now as we're through with this and series and everything, I will talk about that. Before going on to any of the depths, we are going to talk about the concept of potential, everyone. Potential, this term, how much potential you have, how much capable you are, that is nothing but potential. Okay, so when we talk about potential, this term, moreover, a better term would be potential difference that we have to talk about. So when we say potential difference or voltage, yeah, there is a very famous example and you are going to find this example everywhere. I am quoting the same one, reason being it is very basic and the general one, everybody use that example just for the explanation purposes. Okay, I'll talk about a particular potential as well. So when we say and when we talk about potential difference, certainly consider 2 tumblers kept at the same height. Okay, 1 tumbler is having water till a higher level. Okay, you can see. The other one is having water at a lower level. So can you see that there is a difference between the heights, right? Now I am connecting both the tumblers via a tube. Now what will happen? In this particular scenario, when I am connecting the 2 tumblers, tumbler A, tumbler B, via a tube, via a pipe, I will see that, okay, water from tumbler A will start to move to tumbler B. Like this. This movement. And this will continue. From A, the water is going to decrease, and at B, the water will increase. It will continue until and unless both the tumblers, they are attaining the same level of water. Equilibrium, getting equality. Now, Why this is happening? First of all, the first question is, you can see that, ma'am, okay, here the water was at a higher height. Higher height, that means water is kept at a higher potential, moving towards the water kept at a lower potential energy. Link it. Right? We know in this universe, high-low doesn't work. Everybody likes equilibrium. So, of course, water also know moving from high to low. Yeah, high to low. Certainly, let me complete it, right? Yeah, high-low. Remember everyone, whenever we talk about this different scenario taking place, air pressure in air also, or heat transfer from higher temperature to lower temperature, higher potential to lower potential. Yes, here when I am talking about the water being kept, of course, at higher potential and moving towards low potential. If both the beakers, they are having equal amount of water, will there be any flow? No, there won't be any flow. Why? Equilibrium already attained. So for this movement or for any flow taking place, yes, there should be a difference. Who will create this difference? In my, I would say, circuit, I know electrons are flowing. How? Who is creating that flow? Yes, your battery, cell. Okay, potential difference or the voltage that we talk about, it is created by your battery or cell only. So when you talk about this term voltage, when you talk about the term potential difference, right, everyone, you are talking about the difference that is there. How? All of you, let me show you that as well. You had a word on the battery, right? Yeah. Two terminals of a battery. There will be a positive terminal, negative terminal. So if there is a positive terminal and a negative terminal, positive terminal is at higher potential, negative terminal lower potential. So electrons are flowing from higher potential to lower potential. Current flow is taking place. Current flow is taking place. How? Because of the potential difference created by cell or the battery. Okay, so this potential difference that is actually taking place. Right, very general, very basic. So all of you, when we talk about potential difference or voltage, it is created by the battery. How? Because the positive terminal is the higher potential. Okay, negative terminal lower potential. From high to low, the electrons are going to flow. Okay, I will go in depth as well. This is the general concept. The general ones, the kids, those who don't want to go into that much depth of it, this is for you. That okay, higher potential, lower potential. Imagine this is a cell only. Okay, positive terminal to negative terminal. Okay, so yes, there will be the flow happening from positive to negative. Okay, from positive to negative. Yeah. Now I say no, positive to negative, certainly here. Okay, taking place. Now let's talk about the general concept. That is the basic one. Those who are getting more curious that okay, ma'am, this is the general one. But what is actually happening? Let me have a word for you also. When we talk about this term potential, this means capable. I had a word with you, all of you, charges, attraction, repulsion. I am having a positive charge. Okay, kept here. So, of course, this positive charge, if I'll bring another positive charge close to it, it will repel. Right? If I'll bring a negative charge close to it, it will attract. Fine. So, I can say that, okay, there is a region around it. Right? See, this is my particle, right? So, there is a region around it. And if I will bring another charge, into that region, then only it is going to attract or repel. Right? I am standing here. I am a positive charge. There is some charge in the other room. Right? So, we are not into that specificity, right? And moreover, not into that region, so nothing will happen. Okay? Although, by far now, talk about this like, okay, this is the region. Attraction, repulsion will take place. Now, potential is nothing but the work done. How? See, this is a positive charge. I want to bring another positive charge close to it. Imagine, you're having two magnets, okay, north pole, you are trying to bring another north pole close to it. You have to apply some work, no, to bring this charge closer to it, else it is going to repel away. Similar way, I am bringing one positive charge close to another positive charge. I have to apply work onto it. So this work that is applied on a particular charge, this is nothing but potential. So in simple terms when you talk, although for the simple ones, everyone, that is the case, okay, higher to lower potential. Yeah, difference is being created. Okay, one is at high, one is at low, so yes, flow will take place. But in general sense, when we talk about potential is nothing but the work done on a charge. Okay, work done on a unit positive charge from bringing it closer from infinity to a particular point. Or I would suggest, take this thing, when you are applying work to bring this positive charge to bring this positive charge closer to another positive charge, the work done that you are doing, that is your voltage, or that is your potential, a simple potential. Okay, and potential is denoted by V. Don't get confused. Don't get confused if you are not able to get this concept. No need to go into that depth. I'm just giving you a small brief onto it. Okay, taking this thing forward, see, I'm talking about a concept, right? Okay, potential difference. I will explain potential difference in both the forms. Okay, easier also and the standard one also. It is totally up to you which one you have to take. Yeah, you have to take the easier one. This one, moving from higher to lower. Yes, ma'am, the charges are going to move from higher potential to lower potential. They are going to do work, right? So, work done upon a particular charge. Ma'am, potential difference. Ma'am, they are going to move, right? Flow will be there, no? Particles are going to move, no? Charges are going to move, no? So some work will be done. So work done by a particular charge is nothing but your voltage. Okay, work done from moving from higher potential to lower potential on a particular charge, that will be your potential difference or voltage. Take this as voltage. Okay, moreover, if you're getting more curious on this, right? If you're getting more curious that, okay, I am having simple terms. Okay, keep this thing very, very simple. 2 points are there. Okay, A and B. Yeah. So, when I am bringing my one positive charge closer to another positive charge, right? So, the work then that I have to do, the amount of work that I will do, that is nothing but your potential difference. Okay, let us not go into that depth because I believe lot of you will get confused with that part. So, you keep your things till here only. Work done on a charge in order for it to move from a higher potential to a lower potential. That's it. Okay, work done on a charge so that it can move or flow from a higher potential to lower potential. Keep your things simple like that. Okay, in depth we are going to move. Yes, I will bring another video for that. Yeah, because yes, some of you will get confused with it. That is why I am not going into that depth form. All of you definitions are static. You have to learn them as it is in exam also. Okay, so now have a look over here. If, as I am telling you, the symbol for potential difference is V, right? So when I say V over here, you can certainly say, ma'am, okay, that's a symbol, but what about unit? Unit is nothing but volt. Okay, volt, but from the formula I can see unit of work done is joule, unit of charge is coulomb. I can see joule per coulomb, right, everyone? So yes, 1 volt is nothing but 1 joule of work when I will do on 1 coulomb charge. Simple. If I am telling you everyone that, okay, let's have a look here only. Have a look. See, I am telling you here the battery is of 12 volt. What I am trying to convey here? Have a look. Potential difference, volt is nothing but work done upon a particular charge. So what you are going to try, or what are you going to imply and try over here? That, ma'am, this is nothing but 12 joule of work done on a particular charge. right? That means my charge over here, have a look everyone. If I want my charge to move from higher potential to lower potential, yes, 12 joule of work is done on this. Then only the flow will be there. Then only this flow I can see, and my electrons are certainly going to move. Okay, higher potential to lower potential. You are always concerned with higher to lower potential. Okay, now simple. 5 joule or work is done on a particular charge. So 5 volt battery, 5 volt cell. This much amount of work is done on a particular charge in order for my charge to move from a positive terminal to the negative terminal. Higher potential to lower potential. Now everyone, see and understand. I believe I'll keep this, okay? So, now we are going to think. Everyone, we know electrons are moving. Have a look on the diagram also. Electron is moving. Yeah, I told you my particles, they should move from a positive, higher potential to lower potential. This should be the direction of current. Yeah, this is only the direction of current, conventional current. This is nothing but the electron flow. This is nothing but an electron being moved. Yeah, electron moving. Okay. So, everyone, how the electrons are moving. All of you now keep this thing in your head when you talk about current. Yes, movement taking place or voltage or potential difference, certainly nothing but it will provide the flow. Okay, potential difference is going to provide the flow, and in your current, yes, electrons are only flowing, but we talk about conventional current, always movement taking from positive to negative, right? Here one thing is very important. When you talk about negative terminal, okay, negative terminal, in my wire, electrons will be there. So imagine negative terminal having electron, wire is having electron, these electrons are going to repel. Yeah? So as electrons are getting repelled from here, that is why electrons are moving in the opposite direction. So when the electron will reach the positive terminal, it is going to get attracted. That is why we say the electronic flow, the electronic current is nothing but opposite. Because in wire, electrons are there and certainly electrons are only going to move. So yes, from the negative terminal, they are going to repel. Okay, and yes, they are going to move. Clear? So when we see that, okay, yes, your movement is taking place from higher potential to lower potential, that is the truth. But talking about electrons, how electrons are moving, they are moving from negative to positive. Why? Electron repel, negative repel. That is why. Okay, and just giving you a gist that, okay, why electronic current is opposite, this is why. Alright everyone, so as we are through with this, so yes, as there is ammeter, we have voltmeter. Voltmeter is nothing but a device that will measure your simple potential difference. And yes, voltmeter is nothing but it will be kept or placed and always placed or connected in parallel. So whenever you will talk about voltmeter, it is connected parallel in the circuit. Right? Why that is happening, why this will happen, yes, I will be having a word on that as well. Ideal ammeter, ideal voltmeter, we are going to talk about that as well. But by far now, device measuring the potential difference, the voltage, you can say, there between the 2 points. Now all of you remember, voltage will always take place between 2 points only. Higher to lower potential, no, so 2 points. Okay, from higher to lower potential. You can remember this by this acronym, high-low. You do know hello? So that high-low, okay, with this acronym. Yeah, now let's talk about some electric symbols and the components that we use and their symbols also. So everyone, when we talk about electric cell, yes, I believe everyone, you are through. It will be a, 2 parallel lines, one will be longer, one will be shorter. The longer one positive, shorter one negative. Battery, connect. Combination of 2 or more cells, that is your battery. So have a look, combination of 2 or more cells. Okay, similar way, switch open and switch close. Have a look everyone, lot of you get confused with this. So open, yeah, open. That means break. Anything open figures, no. Nothing can be contained inside. Similar way, closed. Yeah, closed. Connection complete, path complete. Then you have bulb. Resistor, it is nothing but a device that will offer resistance. We'll talk about that. Have a look, zigzag. Ammeter, circle A. Volt and positive negative is shown. Voltmeter, circle V. Positive negative is shown. I believe till here symbols are clear. These are the simple ones. Now there's a task for all of you. I want all of you to see and have a look upon galvanometer. What is your galvanometer? Okay. What device it is? Have a look onto it and share with me there in the chat itself. Okay, so let's move. Now, there's a question, calculate the work done by a 2 coulomb charge where voltage is 20 volt. Very simple, very direct question, everyone. So, when we talk about voltage potential difference, work done on a particular charge, so that it can move from higher potential to lower potential. Now, work done they are asking. Simple. Okay. 2 into 20. Right? 40 joule will be the work done. Your work done is nothing but a 40 joule. Very simple. Moving ahead. Let's talk about electric circuit. Very simple. Electric circuit is nothing but a closed path in which your current is flowing. So when I am talking about electric circuit, everyone, yes, I am concerned that okay, there are some components aligned all together. Yeah, and this path, through this path electric current should flow. If electric current is flowing, no, I will say okay, a complete circuit, closed circuit. If have a look here, my switch is open. As my switch is open, it is broken, it is not allowing the current to flow through. Certainly I will say the electric circuit is open, incomplete. You use the term, no, incomplete, and we use the term complete. Bulb glowing, certainly my device working. Right? So electric current is nothing but a closed loop through which my current is flowing, and certainly two types, incomplete and complete. Device working, not working, switch open or switch closed, that is going to help you. As I am talking about electric circuit, certainly basic is done. Now we are going to talk about the thing that is Ohm's law. So yes, Ohm's law tells me only one thing. Ohm's law will tell me, and yes, statement is there, you have to learn the statement as it is. It is going to tell you only one thing, that your potential difference will depend upon current. More potential difference, more current. Less potential difference, less current. So, it is telling you that when we are talking about potential difference, it is directly proportional to current. And this thing has been experimentally proved also. How? I will talk about that. Right? As when we say more the potential difference, more the electric current, certainly when we plot the graph, the graph looks like this. Straight line. Telling me that okay, current is more, have a look over here. Current is more, yeah, potential difference more. See? Okay, so when we talk about the statement, have a look. If the physical state of the conductor, that is temperature and the other ones, right, your pressure, everything remains unchanged. Yes, the current flowing through a conductor is always directly proportional to the potential difference. Right? Now, proportionality sign, everyone. We know we never work with this. I have to remove it. So, in order to remove it, I need to introduce an equal to sign with a constant. This R is nothing but a constant called as resistance that I have introduced over here. Okay. Now, you cannot say that, okay, this is universal constant. No, it is a material specific constant. Yeah. So, yes, it is not a universal constant. Resistance. So, my resistance is nothing but simple. It is nothing but the ratio of potential difference by current. Have a look. right? If you have potential difference, if you have current, you can talk about the resistance. I will talk about resistance in depth also. Right now, for Ohm's law, certainly it is nothing but a constant being introduced. Okay, yes, when we say that, okay, there is a graph being plotted, right? How this thing actually happened. So yes, there was nothing but a circuit that was considered. Okay, and a bulb. Moreover, you can say that, okay, current flowing. Yeah, and you're going to keep always, voltmeter will always be there in the parallel. Okay, and you can connect your ammeter here. So let us connect our ammeter also. Now initially they actually saw also that when they kept the current, let me keep current and potential difference values over here. Okay, when they kept the battery, of course, right? So when they kept the battery of 2 volt, they saw that the current passing through bulb or the system over here or the circuit over here is 1 ampere. Then when they increased the value and they added one more cell over here, created one more battery sort of a scenario and kept it 4 volt, the current value increased and it comes out to be 2 ampere, making it 6 volt. It came out to be 3 ampere. So by this experimental view, people and scientists, they also discovered that, okay, when they are increasing the potential difference, when they are increasing the voltage, there is increase in the current taking place. That is how they stated that, okay, potential difference is nothing but directly proportional to current. Right? Now have a look on the graph over here. Whenever we have a graph, everyone, I believe all of you remember the slope of a graph, like distance time graph also you have, right? Speed time graph also you have. It will give you something. Similarly over here, the slope of your VI, that is nothing but voltage and current graph, will give you nothing but resistance. Why? Resistance is nothing, no, but ratio. See, V is equals to IR, right? Resistance will be V by I, right? So if I take the voltage value, if I take the current value over here and I generally keep it by y by x, perpendicular by base, certainly the slope is going to give me resistance only. Okay, so difference in the voltage by difference in the current will give you nothing but resistance. Have a look. Right, let me erase it, the rest of the things. So yes, in exam also questions are going to come and they are going to give you a graph. Okay, they are going to ask that, okay, what is the resistance? So for that and for that particular scenario, you have to take the y. See, you can simply say y by x. Difference in the y by difference by x give you resistance, or tan theta is perpendicular by base, like that. Anything that is comfortable to you. Okay, always remember the graph of V and I will always give you resistance, be it V by I. Okay, yes, Y by X. That is important because yes, in your Ohm's law we are stating V is equals to IR. Okay, it's not I is equals to VR, it's V is equals to IR. Okay everyone, as we're through with this, so yes, it's not 1, this is I. Let's talk about your factors affecting resistance. Now when we use this term, no, we are saying resistance and we are saying factors affecting resistance, certainly we are talking about nothing but an opposition here. Okay, so when you talk about resistance, and so here in the particular format you are getting comfortable with the term resistance as oppose. So here what will happen? Whenever we will talk about this term, you have to think that, okay, electrons are moving through a wire. There are a lot of atoms. Electron is moving, so those atoms and the electrons over there, they are going to, try that, okay, this electron should not move. try to oppose the flow. So this is nothing but your resistance. In resistance, we are getting very, very specific that it is nothing but the opposition offered. So I want to move through a very, very crowded road. The crowd is going to try that, okay, they are going to try that, okay, I'm not moving. Yeah, they are going to say that, okay, you should not move at all. And I will also feel that, okay, I'm not moving at all because of the crowd itself. The crowd is providing the opposition to me. Right? So when we talk about the factors, yes, resistance is going to depend upon the length. Cross section, resistance will depend upon the nature of the material, very, very important, and your temperature. Now let us talk about this thing one by one. Okay, basically length and cross section, they are the major ones that comes into picture. The rest of it, they will tag along. You are having two wires of the same cross section, same width. Okay, now one is a bit longer. Let me make this longer. And one is a bit shorter. So all of you, when I will try that, okay, my electron should move through the wire, in the longer one, of course, not a lot of opposition, right? People are here and there. Here people are here, here people are here. Yeah, they are here and there. So they will try that, okay, I should not move. Right? In shorter length, people are there. Length is shorter. Less people are there, certainly. So of course, you can say, okay, opposition is there, but not that much. So more the length, more is your resistance, more is the opposition offered to you. Clear? Similar way, if I say less is the length, less will be the resistance offered. So the first factor, resistance, is depending upon length. Directly, more length, more resistance. Okay, now let us take one more example. There is one wire of bigger width and the other one of the shorter one. So when I say bigger the width, everyone, so yes, the people, if they are there in a room, they are going to be scattered away. Opposition is there, but not that much. But in a congested lane you are walking, people are here and there, lot of opposition offered. So over here, when area is more, resistance is less. Right? And when area is less, resistance will be more. So can I say resistance is inversely depending upon area? Okay, now taking these two things only, we are going to club it. R directly proportional to length and inversely to area. Remove this proportionality sign. In physics, we never go with proportionality sign. I have to introduce one constant. Make it equal. So, I have introduced one constant, that is nothing but resistivity. Resistivity is nothing but the nature of the material. Resistivity. Okay, let me erase this thing. Resistivity will actually be nothing but nature of the material. How material is there, or what type of material is there, and what sort of material would be there. Yeah, metals are there, certainly some different type of resistivity, insulators are there, yeah, conductors are there. So yes, resistivity will be your nature dependent. Yeah, and this resistivity, rho, material dependent property. One second, resistivity. Okay, as we are through till here, normal ones, let us have a look on the other thing. Now guys, let's talk about resistivity or specific resistance. So as I am telling you that okay, it is nothing but a material specific, right? So over here what will happen? So if I am talking about a conductor, yes, its resistivity will be less. If I am talking about an insulator, its resistivity will be more. How this is happening? Here it is wholly and solely depending on the material. Okay, what type of material you are talking about, it is wholly and solely depending on that. Right? Now to talk about resistivity, first of all there should be a unit. Unit is nothing but ohm meter. How it is coming? Have a look. For resistance, everyone, as I told you, it is nothing but an opposition offered. Yeah, and for resistance we say V by I, right? My SI unit of resistance is nothing but ohm. This is how the symbol is. Okay, if I will provide you potential difference, if I will provide you current, you can easily find out the resistance. Nothing, a simple opposition offered to my flow. Now, when I talk about resistivity, it is a material specific property. Certainly, from material to material, it is going to vary. For the unit of it, I can use the formula R is equals to rho L by A and take A and R on the top, L at the bottom, rho. Keep the units of your normal quantities ohm, meter square by meter. Right? Cancel 1 meter from 1 meter. What will be the SI unit for resistivity? Ohm meter. Right? Ohm meter certainly. So, as we are through with resistivity, that okay, it is a material specific one. For conductors we certainly have less resistivity. Why so? My conductors are going to have free mobile electron, no? Yeah, they are going to easily move away. In insulator, the electrons, they are tightly bound by. So, of course, they are going to provide more resistance. So, in simple manner, you can say conductor resistivity will be less. Free mobile electrons are there. Have a look here also. There is a table in your book. Yeah, so when you talk about conductor, have a look on the conductor and insulator. See the resistivity, everyone. When you will see the resistivity, in silver, have a look, 1.6 into 10 to the power minus 8. This much less resistivity because of free mobile electron. Free mobile electron. So the electrons there in the outermost orbit, they want to move and they will move. Okay, because in metals, I believe you all have seen the size are big of the atom. Similar way in your insulator, the electrons, they are tightly bound. Smaller in size atoms are smaller. They are tightly bounded by the nucleus itself. They don't want anyone to go out. Yeah, if you are going out, certainly, yes, you are going to be a conductor. In insulator, see, glass 10 to the power 10. This much is the amount of resistivity offered. And resistivity offered, that is nothing but material specific property. Okay, material specific. Am I clear with this, right? So when we talk about resistance and resistivity, certainly the difference is there, all of you. How come? Resistance is nothing but the opposition offered. Okay, and yes, resistance will vary. Similar way, when we are talking about resistivity, it is nothing but the property that will take place and material dependent property. Okay, so here from material to material there will be a slight difference in appearance taking place. Moreover, unit of resistance ohm, unit of resistivity is nothing but ohm meter. Okay, now let's have a look on the question. The area of cross section of wire becomes half when its length is stretched to double. How the resistance of the wire is affected in new conditions? So all of you in the question, area is becoming half and length is becoming doubled. The normal formula of resistance is nothing but rho L by A. Okay, now in place of the new things, write down the values, right? So R is equals to, or R dash is equals to rho 2L by A by 2. Right? Now take the 2 up. 4 rho L by A. R dash. Can you see? Rho L by A is nothing but R. So the resistance is affected by 4 times. Simple. These are the only type of questions that will come in your exam. Okay, very simple. Directly what is given, just place them there and try to analyze what the question is trying to tell you. Yeah, now moving ahead. Let's talk about the combination. So when we talk about combination of resistances, certainly this is nothing but a device resistor that will offer resistance. Okay, the external resistance also that will be offered. The external opposition that will be offered. So we place resistors in 2 normal combination. One would be series, the other one would be parallel. Okay, now in order to get the normal and generalized form, we do that. How they are placed, this is the normal actual setup that I am showing you. Yeah, this is how the parallel combination is there, and this is how series looks like. So when we talk about series combination, everyone, as I told you, symbol for resistance. Yeah, in series combination, everyone, okay, more than one resistance is there. So of course, if I will say that, okay, find out the net resistance, how you are going to do that? If I will talk about what is the current, what is the voltage, if you don't have ammeter, if you don't have voltmeter, only this apparatus is given to you, how you are going to solve the question, how you are going to solve a particular scenario. In that particular form, first of all, when more than one resistance is there, we always talk about equivalent resistance or net resistance. Okay, and the format vary. Why? Have a look over here. Okay, my electron, let us talk about current initially. Okay, my electrons, they have to move. Okay, they are moving. Everyone, let us consider two people. Yeah, A and B. A has to move, so yes, A has to move through R1, R2, R3. Right? B has to move from R1, R2, R3. Right? So if I talk about current over here, for current there is only one lane. Okay, like there is no 2-3 lanes by which you can actually move. Yeah, only one path. So my current that will move through R1, R2, R3, that will be same. Right? My current is nothing but flow of charges taking place through a particular path. Path is same, no, so current is remaining same. I will be same. In R1, R2, R3, so can I say I? Okay, now talking about potential difference. Kids, potential difference will be between 2 points. Yes, my charge moving from one point to another, high to low. Have a look. For R1, everyone, see, for R1, my charge will move from A to B. Right? See, point A to B. Now, for R2, when the charge is going to move from high to low, it will be from another 2 points. Right? Similarly, when the charge is going to move from higher potential to lower potential, certainly from R3, the points are different. Have a look. Getting me, everyone? So, over here, when my charge needs to flow from higher potential to lower potential, the points are varying for each and every component over here. Higher to lower here, now higher to lower, then higher to lower. Right? If you want to consider, so you can select from higher to lower, higher to lower, higher to lower, like that also, but it's better to take one component each. Yeah, so voltage or potential difference will be different for each and every resistance over here. Right? So we are going to say that over here, yes, the voltage is different. For R1, voltage will be V1, R2, V2, R3, V3. Okay, so how you are going to talk about what is the net resistance or what is the equivalent resistance? There is a derivation, I am doing that also. What is the total voltage? V, right? And in order to get the total voltage, I will add all the voltages, right? So, V1 plus V2 plus V3 will be the total voltage. Now, in place of V1, can I write down I R1, I R2 plus I R3, right? And in place of V also, I am writing down I R equivalent, because that is the net, R net or R equivalent. Okay, take I common, R1, R2, R3, and take I here, R equivalent. Cancel out I from both the sides. In order to find out the net resistance or equivalent resistance, whenever the resistances or resistors certainly over here, they are in series, you just have to add them. Okay, for example, if R1 is 2 ohm, R2 is 3 ohm, R3 is 1 ohm, what is the R equivalent? What you are going to do? They are in series, directly add them. 6 ohm. Okay? Yeah, this is how we do. In series, Yes, net, this question will come, that what is an equivalent resistance in this combination, in the series combination, or in the diagram. So yes, you have to first see whether it is in series or parallel and move ahead. Okay, in series all the resistances, they are added all together. Yeah, now let's talk about parallel. Parallel means it's not one after another. It will be a combination where all the particular components, no, they are connected from one point to another one. Sharing it. Have a look. See, point A to point B. Right. Now, let's talk about current. Current would be flow. Okay, flow. I am depending on path. When the current is coming over here, current is saying that, okay, I am having 3 path. 1, 2, 3. I can move anywhere. So current, of course, the current will say, okay, some of it will move in 1, 2, and some of it will move in 3. Right? You see, the actual current that was coming, right, is getting distributed. It's like a marathon having 3 paths. So some of them they are going to move in A, some B, and some in C. Particularly some in D also. Right? So current will say that, okay, some of it will move in A, B, and C. So over here, the current is changing. The net current will come out to be when you add the current in all the 3 paths. Okay, talking about voltage. Voltage is okay from moving higher to lower between 2 points. Have a look. For R1, the 2 points are this and this, A and B. Okay, let me just mark. Right? For R1, A and B, R2, A and B, R3, A and B, all of you. Have a look carefully. My higher point to lower point movement taking place from one point to another, the points are remaining same, voltage will be different. No, voltage will be same. Right? So over here the voltage remains same. Because the particle has to move, the work done on a charge moving from one point to another, higher point to lower point, higher point to lower point, same. Right? So over here voltage is remaining same. So I can say V voltage will be moving through R1, V voltage will be moving through R. V voltage potential difference in R2 is V. Potential difference, not moving certainly, potential difference there on R3 will be V. Okay? Right? So don't use that term moving. I was just trying to convey, right, that what is actually happening. Yeah, potential difference there in R1, V, potential difference in R2, V, potential difference in R3, V. Okay, now let us derive that how I will find out the R equivalent. See, in place of I1, can I write down V by R1, I2, V by R2, I3, V by R3. I hope you all remember Ohm's law by far now, so this is nothing but the same. Okay, and V by R equivalent, the net. Take V common, 1 by R1 plus 1 by R2 plus 1 by R3, and that is V by R equivalent. Cancel out the V. What you are going to get? 1 by R equivalent will be equal to 1 by R1 plus 1 by R2 plus 1 by R3. So that means whenever you have to find out R equivalent in parallel scenario, you are going to use this formula. Right? Let me show you also. We will take only 2. Okay? So my R1 is 1 ohm and R2 is 2 ohm. I want to find out the R equivalent. Yeah? So 1 by R equivalent will be 1 by R1 plus 1 by R2. Okay? 1 by 1 plus 1 by 2 is 1 by R equivalent. Okay? Now solve this. 2, 1, 3 by 2. Kids, now remember 3 by 2 is not the R equivalent. Why? Because this is 1 by R equivalent. Right? You have to inverse it. The value of R equivalent will come out to be 2 by 3 ohm. The important step, the most important step that we talk about. Okay, so at the end, a lot of kids actually get confused and they don't inverse the whole scenario, but you have to. Alright, now let's solve a question. Okay, I want you all to solve this question by yourself also. Okay, and then we are going to have a look onto it. R1 is 4 ohm, R2 is 1 ohm, R3 is 3 ohm, R4 is 6 ohm, R5 is 2 ohm, and 12-volt battery is there. Okay, this is the whole combination. So all of you, now you are getting confused that ma'am, these two are parallel, these two are parallel, these three are parallel, right? And how we are going to solve this question? So all of you in this question, first of all, you have to break the cases. Okay, deduce it into the smaller manner and then try to attempt it. So try to attempt it by yourself as well. Try this one, everyone. So all of you here have a look. R1 is given to us, that is 4 ohm. R2 1 ohm. R3 3. R4 6 ohm. R5 2 ohm. Okay, now break this thing. First of all, talk about R1 R2. They are in parallel, no? 1 by R1, 1 by R2, 1 by R equivalent. Okay, 1 by 4 plus 1 by 1, that will give you 5 by 4, but R equivalent will be 4 by 5. Okay, so in place of this parallel, you can simply draw one resistance like this, 4 by 5 ohm. Right, now the 3, 1 by R equivalent will be 1 by 3, 1 by 6, 1 by 2. Okay, simple. Take the LCM. I believe by far now you all are comfortable with LCM because you have done the first chapter also. Okay, 6. 6 by 6, that turns out to be 1 by 1. R equivalent is 1. In place of all the 3, you can just draw a simple single 1 ohm. Now if I draw this circuit right in the easier form, no, you will get 1 resistance here and certainly here. Okay, so 4 by 5 ohm, 1 ohm. These two, they are in series. So what you are going to do, directly add them. So doing it, R equivalent, (9 by 5 ohm). Okay, right? Simple LCM, no? Take LCM and then you will be able to do it. Yeah, so we are getting 9 by 5 ohm as the total resistance. What is the total current? Everyone, total current, V is equals to IR, I is equals to V by R. You have voltage, you have your resistance, right? 12 by 9 by 5. Okay, simple. Okay, 3, 3, 4, 20 by 3, 6.66 ampere. I hope the question is clear, everyone. Okay, here, yes, R equivalent will be directly added. They are in series altogether. And total current, I is equals to V by R, you have reduced it down to the simpler level. So you can directly use V is equals to IR. Okay, this is how the questions they come, and yes, in exam. So now, as we are through with this, so everyone, whenever you get any question like this, you know, yeah, this condition you are getting, what you are going to do, you are going to deduce the circuit into easier and the last format and make it into the easier one. Okay, see, this is in parallel. See, R1, R2 parallel. So yes, you are going to 1 by R equivalent will be 1 by R1 plus 1 by R2. Right, from here you are going to get R equivalent. Then this R3 is in series, then you are going to directly add it. Okay, deduce it down to the normal general circuit like this, and you will be able to solve the question, the last R equivalent. Okay, everyone, clear? Now let's talk about heating effect of electric current. What is heating effect, everyone? So when we talk about, okay, current is flowing through a wire, yes, the flow or the charges, they are going to get opposed. As this opposition is taking place, no? Yes, because of this opposition, certainly the particles or the charges, they are going to get a bit disturbed. Yes, they are going to get kinetic energy, and as they are going to get this kinetic energy, these particles, they absorb this kinetic energy in the form of heat. So when we say heating effect of electric current, I believe you have done this in your class 7th as well. So what is happening? Yes, my here energy, or certainly let me say that okay, the work that we are doing, that is simply getting converted, the work that we are doing, no, that is simply getting converted into heat energy. Okay, so or in simple format, heat energy is nothing but when particles are flowing through a wire, the wire is going to get heated up. Why? Because of the resistance offered. Simple. Okay, so here what is happening? Yes, the material is going to get heated up. Now I am saying work, right? Remember, V is equal to W by Q. Okay, in the place of this, I can write down work done is nothing but potential difference into charge. Will that be fine? Of course, right? We can. Alright, now what is your charge? I is equals to Q by T, right? In the place of Q, I can write down IT. Will that be fine? Right? In the place of V, can I write down IR? Now have a look. I square RT, that is nothing but work, that will be nothing but heat energy. So the formula that we talk, H is equals to I square RT, it is actually coming up from the work done only, everyone. I stated this term, no? The work we are doing, that is converted into heat. Yeah, the energy. So yes, over here also energy and work, they are interrelatable. You can use these two terms irreplaceably, right? So over here when we say that okay, heat over here is going to depend upon the current, the square of the current, the resistance and the time, it is because of this format. Okay, more the current, more will be the heat, more will be the resistance, more will be the heat. For more time, yes, more will be the heat. So quantity of heat generated in a conductor, it depends upon three factors. Yes, your current, square of current, resistance and time. Okay, how it came into picture, I have shown you. We use heating effect of electric current all around us. We use it in bulbs, we use it in safety devices like fuses also. Okay, moreover, we use it in our geysers as well. So when we talk about bulb, yes, the filament is here, and this filament, tungsten filament, it is made up of a very, very thin wire. Yeah, coiled. Alright, so what will happen when current is going to flow through it? Here the wire is going to get so heated up as it is going to give out heat and light. Heat and light, they are like sisters only. Right? The filament of the bulb is generally made up of tungsten material. Why? Having melting point high. Melting point is high, because out a lot of heat. Okay, so yes, if less amount of heat is passing through it and it is getting melted out, so no use for me. That is why high melting point. Right? Talking about fuse, it is a safety device, everyone. When we talk about fuses, it is going to protect my house. What will happen? Large amount of current is going to pass through it. So we certainly say that okay, the fuse wire is going to melt and my whole circuit will be safe. My devices are going to be safe enough. That is why. Okay, so over here when we talk about electric fuse, it is used to protect the electrical appliances from higher voltage, if any. Electric fuse is made up of metal or alloy of metals such as aluminium, copper and iron, lead. Okay, in case of flow of higher voltage than specified, fuse wire will melt and your appliances will be safe and sound. Right? Very easy topic. Yes, at times numerical can come from the formula as I have derived, everyone. Okay, moving forward, taking this thing forward, certainly we are going to talk about electric power. Power, how much power you have. Right, that is this electric power. So electric power will be nothing but work done by time. That is rate of work done by time. How much work you can do in a particular time, that will be your power. You can do lot and lot of work in less amount of time. You are so powerful. Similar way, work done upon time is nothing but our electric power. SI unit will be what? Okay, now yes, we have another formulas for power as well. Everyone have a look over here. Okay. Right now we have done this thing. So Work done will be potential difference into charge. Any problem? No, right? Place it over here. Q by T is nothing but current. Very famous formula. This is how it is derived. From the general sense, work done by time, you are getting power is also potential difference into current. Of course, you can get one more thing. See, if in place of V, this V, I will write down IR. Any problem? No, right? Into I. Power is nothing but current square into R. Similar way, power is equals to voltage square by R. So these are the 4 formulas. This is a standard one. From this, you can talk about the other. Very simple. In simple terms, power will be how much work you are able to do in a particular amount of time. That is your power. SI unit will be watt. Okay, there is one more tiny topic when you talk about energy. See, energy or the commercial energy, the commercial unit of energy is nothing but kilowatt hour. So for that purpose, we use energy is nothing but power into time. Work is nothing but energy only. Okay, you can write this down like. Okay. So energy will be power into time. Yeah. Now, how the unit, the commercial unit of kilowatt hour you are getting. Power you have to take in kilowatt. Time in hour, kilowatt hour. Okay, that is the standard and the general one. Okay everyone, so I believe till here the things are clear. Now to use this, of course, we are going to do a numerical. An electric iron having a rating of 750 watt, that is nothing but power given to you. Okay, voltage given to you. Current P is equals to VI, right? 750 by 200 will be I. Find out. Tell me the current value in your chart, everyone, ampere. Okay, exam level question. Next one, the resistance of its heating element. Anyone you can use. P is equals to I square R or use V square by R. Any of it you can use, any of it. Okay, this is your homework. You are going to do it on your own. Share the answers with me in the chat. And I believe till here the concepts are clear, all of you. Okay, I know this chapter is a bit big, but certainly we have completed it. And yes, I will be seeing you all in the coming up videos also. Keep on practicing. Thank you so much, everyone.